going on, Mr. Brevard? It's your favorite group, Luci, Tajareeh, and AJ, and today we're gonna talk about the binomial theorem. So what exactly is the binomial theorem? It is an easier way to expand a binomial than doing it by hand with a exponent greater than 2. It saves a lot more time than just factoring it, or foiling it rather. The condensed form for it is x plus y to the m power equals n sigma k equals 0, where n choose k, x to the n minus k, y to the k. Or it's easier seen here. And the expanded form is x plus y to the n equals p0 x to the n plus p1 x to the n minus 1 y plus p2 x to the n minus 2 y squared. And then you'll just keep going until you get p to the n minus 1 x squared y to the n minus 1 plus pn y to the n, or simply wrote here, where p is the numbers in the n row of the Pascal's triangle. And now there are also some algebraic patterns that go along with it. The first term and the last term are both x to the n and y to the n. The power x decreases by 1, whereas the power of y increases by 1, and the coefficients for each are both symmetrical. Tajareeh is going to explain about who came up with the binomial theorem.
Okay, I'm guessing. Okay, who is Pascal's triangle named after? Where is he from? And when was he born? Did he invent the triangle? Blaise Pascal was born June 19, 1623. He was from Clermont-Ferrand, France. Though named after Blaise Pascal, the Pascal triangle was used by other mathematicians before his birth. It was discovered by the Persians and Chinese during the 11th century. Okay, there are many patterns in the Pascal triangle. I'll be talking about 3. The first pattern that we have is the horizontal sums, which is this, okay, over here. For that triangle, every time you horizontally add the numbers, for each row, the sums are doubles of powers of 2. Okay, so let me show you. Like that equals to 1, 1 plus 1, 2, and so on. Okay, the next triangle is the odds and evens, which is as shown. For this triangle, if you were to color in odd numbers, a different color from the even numbers, you would create a Sierpinski triangle, which is a repeating pattern of triangles. The third and last pattern we have is the diagonals, which is this triangle. For this triangle, the first diagonal is all ones. The second is just counting numbers 1, 2, 3, etc. The third has the triangular numbers. The fourth has the tetrahedral numbers, and that's it. Goodbye.
Hello, Mr. Brevard. So now that we got a little background information on Pascal's triangle and the binomial theorem, I'm here to expand some equations and find the nth term of some expressions that are not expanded. So I'm just going to set this down here. You can take a look. So as you can see here, we have the parent equation x plus y to the nth power equals sigma n over k equals 0. N choose k, x to the n minus k power times y to the k power. And it's important to note that n choose k is just n factorial over k factorial times n minus k factorial. So the expression we're going to expand is m plus n to the 5th power. So we replace n with 5, k will still equal 0, and n choose k is 5 choose 0, m times to the 5 minus 0 power, and n to the 0 will just equal m to the 5th. Then we plug in when k is equal to 1, sorry. So n minus k is just 5 minus 1, we get m to the 4th, and n to the 1st power, and so on. As you can see, we have m to the m cubed and n squared n cubed, m times n to the 4th power, and n to the 5th power. But whenever we are solving or expanding one of these equations, we always have to solve for n choose k, and we have to multiply that. That is going to be the coefficient of our expression. So 5 choose 0 is simply 5 factorial over 0 factorial times 5 minus 0 factorial, which will just be 5 factorial over 5 factorial, which is just equal to 1. 5 choose 2 factorial. Oh, sorry, that was 5 choose 0. So 5 choose 1 factorial will just equal 5. 5 choose 2 factorial will just equal 10. 5 choose 3 also equals 10. 5 choose 4 equals 5. And 5 choose 5 equals 1. So this is also another pattern that Tajareeh touched upon in her last presentation. So now we have to multiply the coefficient, which we're getting from the n choose k, times each term. So before we actually get our final equation, we are going to multiply the 1 from 5 choose 0, the 5 from 5 choose 1, the 10 from 5 choose 2, the 10 from 5 choose 3, the 5 from 5 choose 4, and the 1 by 5 choose 5. And then you get m to the 5th power plus 5m to the 4th power times n plus 10m cubed n squared plus 10m squared n cubed plus 5m n to the 4th power plus n to the 5th. So that is just one way you can expand an equation. That's just one example. Now I was tasked with the how do you find the nth term of an expression. So now we have 4x minus 3 to the 8th power, and we have to find the 5th term. So one way I found how you have to do it is, this is the c, this is what we're trying to find, this is going to be our coefficient actually, and we have our n here and our k here. We have to multiply that by 4x to the 4th power, and we have to multiply that all by the negative 3 that we're taking from here, and n minus k, which will just be 4. So when we solve for c, it's essentially just back to the n choose k, back to the n choose k formula. So n factorial over k factorial times n minus k factorial, which will just be 8 factorial over 4 factorial times 4 factorial, which actually comes out to 70. So then when we multiply, we get 70 times 4x to the 4th times 81, which will simply equal 22,680 x to the 4th. So when we are finding the 5th term of 4x minus 3 to the 8th power, it is just 22,680 times x to the 4th. Thank you for watching this presentation, and your favorite group members are out.
Since AJ went so quickly on that first example and really mastered the task, I thought I would show the true beauty of the binomial theorem and take it a little slower on the second example. So the prompt I was given was expand 2x plus 1 to the 4th. So first I should put it into the binomial theorem and plug it in. So 2x plus 1 to the 4th equals 4 sigma k equals 0, x to the 4 minus k, b to the k. And when you expand that out, it would be 4 choose 0, 2x to the 4th, plus 4 choose 1, 2x to the 3rd times 1 to the 1st power, plus 4 choose 2, 2x squared, 1 squared, plus 4 choose 3, 2x 1 to the 3rd power, plus 4 choose 4, 1 to the 4th. Now, this 4 choose 0 stuff, let me explain that a little further. So n choose k, or 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, is simply just n factorial equals k factorial n minus k factorial. What the hell does factorial mean? Factorial is simply, okay, so in this case n would equal 4. So if n factorial would equal 4 factorial, which would be 4 times 3 times 2 times 1. So, with that in mind, 4 factorial over 0 factorial times 4 factorial, well, that would simply equal 1. That's just saying same thing as 2 over 2. 4 choose 1 would be the same as 4 choose 3. 4 factorial over 1 factorial times 3 factorial. And the common factors they have is 3 times 2 times 1, which would equal 4. 4 choose 4 would be similar to 4 choose 0 because they have the same values in the numerator and denominator. 4 choose 2, on the other hand, is the greatest one because 4 factorial is 4 times 3 times 2 times 1. 2 factorial times 2 factorial would be 2 times 2, which would equal 4. So that leaves us with 3 times 2 times 1, which would equal 6. So, after discovering all of the choose numbers from 4 choose 0 all the way to 4 choose 4, you plug it in. So this would equal 2x to the 4th plus 4 times 2x to the 3rd times 1 plus 6 2x squared times 1, because 1 squared is 1, plus 4 times 2x times 1, because 1 cubed is still 1, plus 1, because 1 to the 4th is still 1. And then after solving the parentheses, you would just be left with 2x to the 4th plus 4 times 2x to the 3rd plus 6 times 2x to the 2nd plus 4 times 2x plus 1. And after distributing each parentheses, you would be left with 2x to the 4th plus 8x to the 3rd plus 12x squared plus 8x plus 1. And now we're going to go on to how to find out the nth term without expanding it and doing this much work. It's actually a lot simpler.